Hello and welcome to the last Linux lecture. Today we're going to cover actually quite a few topics. Three of them are deeply connected. One of them is a little bit of an old bool out. The three deeply connected ones are block.io, file systems, and pipes. Signals are a little bit of an oddball here, but we thought that it doesn't make sense to actually finalize the course without even touching upon the concept of signals in Unix systems. I'm making a disclaimer here that th there are some new sources that I've used in this lecture. These includes the excellent lectures by Dan Porter, and also a book that you can access via the UMass library for free. It's actually a really book, so you can even access it on their website, I think now for free during this period. So we'll start with discussing how Linux handles block devices. And you have covered quite a bit of information already about block devices. Block devices are basically hardware devices that are distinguished by the random access of fixed size blocks of data. That means that there is no requirement for you to access the data in sequence. There are many block devices that exist today. Some of them are you actually are central to your computer, like your hard disk, Blu-rays, flash memory, CD-ROMs, and so on. In Linux, all these devices will be mounted to the file system. I believe that is actually similar to Minix, if I'm not mistaken. Now, as Prashant has touched upon, there are two kinds of devices in large I/O devices. One of them is the character device, and the other one is the block device. Character devices have very few possible I/O states. For example, your keyboard has basically the states of the number of keys and maybe some other combinations if you click shift or function or the function key, or if you have some special key combinations. But at the end of the day, there are finite combinations, and these finite combinations are actually not that large. The kernel thus has no subsystem to manage the character devices, and character devices management is mostly handled by the drivers for these devices. However, block devices are a different story, because they basically provide you with an infinite combination of how you can put the data, how you can manage the data, what blocks you read, and so on. There are just too many combinations for the system to leave this for different drivers. So Linux actually provides a whole block device subsystem, and the main goals for this subsystem is to increase the overall throughput of the devices, decrease the latency of these devices, to have safety against failures, and to have fairness. And fairness is an important concept, especially when we talk about I/O scheduling. The big picture of today's lecture, well, there is the virtual file system that we'll cover in a little bit. Lower level file systems like the extended third, extension, and ext4. We're actually going to touch upon them very lightly today. Then there's the page cache, which we covered in the last lecture. Then the block device and the I/O scheduler, both of which we will actually start with the lecture. And then there's the actual driver for the disk or for whatever block device you're using, and that driver basically handles all hardware translations if needed, and handles special idiosyncrasies about the different devices basically. So this is the anatomy of a block device. You basically have, and for historical reasons, hard disks used to be basically consisting of like magnetic disks, where you had a motor that actually rotates, and you basically divided the hard disk into sectors and into segments, and so on and so forth. So historically, this was the figure on the right hand side is the historical figure of how all these devices were thought of. So a block device basically has the smallest addressable unit, that is called a sector. And the sector, as I said, comes from the history of how hard disks were. Sector sizes vary between devices and architectures, but they are typically between 512 bytes to 4 kilobytes. These are called by some people also, the sector also has a second name and a third name, and these are device blocks or hard sectors. The software, however, does not have the same hardware limitations, because the hardware, the hard disk, it had a physical actual limitation on how things are, and similarly all block devices are like that. There are physical limitations, right? The software, on the other hand, does not have the same limitations. So the software imposes its own smallest logically addressable unit, and that is a block, basically. The kernel performs all disk operations in terms of blocks. The block size can be no smaller than the sector, so the smallest possible block that you can get is the sector size. So if the sector size is 512 bytes, then this is your smallest block. If it's 4 kilobytes, then your smallest block is 4 kilobytes. The block size can be a multiplier of can have multiple times the equivalent of the data stored in the sector. So it can be 2 megabytes, for example. Okay. The kernel basically requires that a block be no larger than the page size, and that's why I actually said 2 megabytes. So if you have huge pages, as we have discussed in the last lecture, then you can have larger block sizes. But if you're sticking with the largest page size that you actually have in traditional Linux, then we are talking about 4 KBs or 8 KBs, 16 KBs possibly. These software blocks are sometimes also called the file system blocks or I/O blocks. So basically, the way that this system that the interaction between the physical block I/O device and the kernel, basically the communication between these two happens through buffers and buffer heads. A block, basically, that is being read by the kernel is stored in memory, and then that block is stored in what we call a buffer. The buffer basically serves as the object that represents a disk block in memory. So you have a sector that is on the actual physical device, and then the kernel basically aggregates a group of sectors saying that this is my block, and then each block is mapped in memory or to a buffer in memory. A single page can hold one or more blocks in memory, right? Because if your block size is small, then one memory page can actually be multiple times your multiple blocks in your system. Sorry, forgive me. The kernel requires some associated control information to accompany the data, obviously, because you have basically now some mappings between an actual physical device that which has some sectors and then some blocks, and then you have now another level of indirection, which is the buffer. So each buffer is basically associated with a descriptor, or what we call a buffer head. The buffer head definition is in the link that you see, and the purpose of the buffer head is to describe the mapping between the on-disk block and the physical in-memory buffer. This basically acts as a descriptor of this buffer to block mapping in the data structure and this is the main purpose, the only role of the data structure in the kernel. Now, traditionally, the buffers and buffer heads had a lot more value into the system. They were actually used to manage the old block devices, but this has changed with the introduction of what we will call of what is called the bio struct that we will talk about shortly. This is how the buffer head structure is in the kernel, and basically it has a few pointers, a few structs, and it tries to map the blocks on the actual physical device to the buffers that exist in memory. So now we shift our attention to the bio layer, and the bio layer basically is something that is the actual interface between the file system and the actual devices. Now let us look at the bio layer in more details. First of all block devices in Linux are represented by a general structure that is called gendisk. It's basically a generic disk structure. It's supposed to encompass a very generic view of all the different block devices that can exist. The bio layer itself carries read and write requests and assorted other control requests from the block device past the gendisk and onto the driver. So the bio layer, the bio layer basically acts as an intermediary layer between the gendisk, the generic definition of the device, and the actual device driver. A bio identifies a target device, an offset in the linear address space of the device. So it basically identifies which device are you trying to read or write to. The offset in the address space, basically what data you're trying to read, the size of the data you're trying to read, and some memory where the data will be copied to or from. Each block IO request, so each request that is issued to the bio layer is represented by a bio structure that is called struct bio. Okay, and this is a data structure that basically tries to map what pages, what parts of the device are you going to read or write from. Okay, this is basically the basic container for block IO operations. Okay, and it represents the block IO operations that are active as a list of segments. A segment is basically a chunk of a buffer that is contiguous in memory. So the sole purpose of having this struct is to actually try to represent all active IO operation as a list of segments, and each segment is basically has some data that needs to be written. The actual individual buffers need not to be contiguous in memory, so you do not need basically to be writing from pages that are next to each other in memory. You might be writing from different pages, different bits and pieces to your physical device. And the bio structure provides the capability for the kernel to perform block IO operations or even a single buffer from multiple locations in memory. So it's basically it's the way that with which the kernel can actually write to and from and read from the devices, the block devices. And this is how the bio struct looks like. It's actually defined in blk_types.h, and a lot of its control mechanisms are in bio.h. The book, the old book, actually the Robert Love book, describes it in an older version of the data structure that is obsolete, and they even point to a different file. So this is the new up-to-date structure that exists in today's Linux. So important fields in the struct. The first one is the BIOVEC, which is an array of BIOVEC structures. These structures are used as lists of individual segments in this specific block I/O operation. Basically, each BIOVEC is treated as a vector of the form page, offset, and length. Describes basically a specific segment that you're going to read or write. The physical page where it lies, the location of the block as an offset into the page, because you might not be writing the entire page, you might be writing a single word in that page back to the block I/O device, and the length of the block starting from the given offset. So it basically it gives you an array of the different things that are you need to read or you need to write to the block I/O system. A deeper bio understanding is beyond the scope of this lecture, but however there is a very nice reading. I point you to that reading that basically describes the layer in more details, and it's much more up to date compared to the book. Actually, most of the stuff in this lecture is very different from what the book describes. Some very general ideas are still there, but most of the stuff you actually will find on lwm.net or in some other blog posts or sometimes in the kernel code itself. So how are BIOS actually used in the kernel? This is actually done using request queues. Basically, each block device maintains request queues to store their pending block I/O requests. Okay, and each of these requests is represented by a request descriptor. There are two things to note here. One of them is that you have the actual request, and each request is represented by a request structure that is defined in blk dev.h. But also you have a request queue that basically is a doubly linked list that maintains all these requests together. This is basically for each device to know what are the pending requests for it to process. So as long as a request queue is non-empty, the block device driver associated with the queue grabs the request from the head of the queue and submits it to the associated block device. So the idea here is basically to have a queue of tasks for each of these block devices to be able to process them. Now you can have two kinds of queues. The first one is what we call a single request queue. And the single request queue, what we're saying is basically for each block device, there's one single queue from which the device needs to process the different tasks, the different I/O tasks, read and write tasks, basically, or modify tasks, whatever these are. Traditionally, most storage devices were made up of a set of spinning circular platters with some magnetic coating. So basically, in these magnetic drives, you typically had a head that would move, seeking and rotating until it reached a certain part in the device to read from it or to write to it. Such a device can only process a single request at a time, basically, because, well, you have a single head, and there is a substantial cost in moving from one location to another, as you have discussed in the Minix block device lecture. Now you can build a scheduler to schedule basically what or which requests can get processed first, and this is what we call single queue scheduler in this case, and the single queue scheduler, what it does is basically it collects multiple BIOS, basically multiple requests to read and write, and tries to basically zip them to represent contiguous operations into a smaller number of requests. So basically, if you're trying to write to two sectors that are next to each other on the disk, then what this algorithm would try to do is basically it will try to make sure that you do both operations next to each other, so that you do not need to seek a lot and you do not need to rotate a lot. And instead of basically going into these doing these operations into whatever order they came with, because then you will have to seek and rotate, and maybe one of them will be on one end of the disk and the other one will be on this other end of the disk, but then you will have to go back to the first end of the disk for the next write read operation. So this is one key task for when you're building such a system over a single queue. The other thing is that you want to queue these requests in an order that minimizes seek time while not delaying important requests unduly. So it doesn't make sense, for example, to even if you're going to do a lot of seek and rotate, to delay real-time applications, basically applications that should be highly responsive, because you're trying to basically reduce the numbers of seek and rotation time. For interactive applications, you want the application to be responsive rather than having higher throughput at the disk. You do not really care as much about your disk throughput as long as your application is functioning in the way that you would like it to be. And actually trying to solve this problem is the source of all the complexities in I/O schedulers. You also need to enable the underlying driver to be able to pick some of these requests or to feed the underlying driver with these requests to be scheduled on the block I/O device. And you want the driver to be able to notify the queuing layer, the scheduler, basically the single queue scheduler, of any updates in the driver, basic notifications when these requests are complete. There are also many reasons for having multiple request queues today. So single request queues, they stemmed from the fact that, well, we had magnetic disks, but now, for example, with devices such as SSDs, you can actually process multiple I/O requests in parallel, because you no longer have a head, you no longer need to seek, and you no longer need to rotate. As also we get more and more processing cores in our system, traditionally what you would need is basically, if you had a single queue, is that this queue will need to be locked when one of these processors would try to do any changes to that queue. Basically, if any of the cores try to schedule an I/O operation, it will need to acquire a lock to access that queue. Now, if you have one core or two cores, it works okay, but if you have 16 or 32 cores, it becomes an issue, because sometimes that queue, the request queues for I/O can become a bottleneck, because all 32 cores are trying to access the queue, and then they will need to acquire spin lock to do that. So Linux introduced the concept of software staging queues, and software staging queues are basically queues that can be added their software queues that are added for each of the CPUs. So if you have 32 CPUs, then you'll have 32 software staging queues. And requests from each processor are added to these queues. So each processor adds to its own queue. and then each processor does not need to lock on for all other 32 processors at once. And then based on what hardware you have, you can even translate these 32 software queues that exist for the cores to 32 block driver queues. So for example, if you're running with SSDs and NVMe, you can actually process all 32 requests in parallel. For some other devices, these 32 CPU software queues need to be basically zipped into one single queue for that device. So this way you actually enable the CPUs not to block as they were over the I/O devices, and you make it a problem to the driver itself to actually handle these 32 CPU queues, these basically software queues. You can read more about this in this LWN post. So now that we have established the fact that there are queues in the system, now you need to schedule how these requests get handled. And similar to process schedulers, you have also an I/O scheduler. And the I/O scheduler is between the page cache and disk. Okay, it lies between the page cache and disk, and you have requests in the form of tuple. Basically, you have a block number, read or write, and a buffer address. These write requests can be reordered based on some heuristic. For example, I can say that, well, I'd like everything that lies in two adjacent sectors to be written at the same time. And the rationale is that I/O is very slow compared to most other system components. And even on SSDs, you still need a multi-queue I/O scheduler, because maybe you will end up with too many CPU queues that the SSD device can still not handle. So you will need to basically piggyback things and make sure that the multi-queues are handled correctly with an I/O scheduler. The I/O scheduler, from a scheduling point of view, what it does is that it divides the resources of disk I/O among all pending block I/O requests in the system. It does that by merging and sorting of pending requests in the request queue, basically trying to find requests that are touching areas that are next to each other, for example, in the device, in the block I/O device. These I/O schedulers require some understanding of the disk model that they are working on or that they are dealing with, and there is an inherent knowledge that these I/O schedulers will be actually unfair to some requests at the expense of improving the overall performance of the system. There are multiple I/O schedulers available. In fact, there are probably as many I/O schedulers as there are process schedulers, if not more. However, many of the I/O schedulers, including almost all of the I/O schedulers that are described in the book, are now obsolete in the first and the second book, both of them actually. But looking at how this evolved is actually interesting. So we're going to describe some old and new hardware scheduler. And as we said, they basically all of these I/O schedulers operate on the request queues. So one of the very first schedulers, we'll just jump into that, is the elevator algorithm, which was developed by Linus for kernel version 2.4. And the idea was simple. When a request is added to the queue, it is first checked against every other pending request to see whether it is a possible candidate for merging. So basically, whenever you get a new request, you try to actually make sure that that you put it in the queue in the correct order. So basically, you put it next to the memory location that the block I/O location that it is going to be closest to. If a suitable location sector-wise is in the queue, the new request is inserted there. This basically keeps the queue sorted by physical location on disk. If no such suitable insertion point exists, the request is inserted in the tail of the queue. This is the code for the elevator algorithm. It actually still is supported in the Linux kernel. So the first obsolete kernel that we're going to talk about is the Noop scheduler. The first obsolete kernel scheduler, IO scheduler that we're going to talk about is the Noop scheduler. And it was based on the elevator algorithm that we just described and where the code we just also pointed to. The idea behind the Noop scheduler is that it provides minimal sorting of requests, never allowing a read to be moved ahead of a write or vice versa. This allows one request to overtake another if in line with the elevator algorithm. So you make sure that reads do not overtake writes, so no read happens before writes, and then you use the elevator algorithm for merging between requests. Apart from this simple sorting, Noop is basically a first in first out queuing system. Okay, this is the old code. It's actually hosted on the Spotify GitHub, and this is, as I said, an obsolete scheduler. The second one we're going to talk about is the deadline IO scheduler. One of the issues with the Noop scheduler and the elevator algorithm is that since they try to sort of place requests where they should come, looking only at their spatial characteristics when it comes to the block IO device, this means that some requests that, for example, lie far away in terms of sectors that require lots of seek time and lots of rotation time can end up starved or can end up severely delayed. The deadline IO scheduler was designed to actually fix this, and the deadline collects batches of either read or write requests that were all submitted at close to the same time. The idea is pretty simple. You maintain a request queue sorted by physical location on disk that is used for scheduling as long as a certain time quota is not expired. Once filled, this queue is used to schedule operations. So you have a queue of a very limited size, and you try to sort things into this queue based on the spatial characteristics of the block device. Okay. However, you also have a timer, a deadline running on that queue, in order to basically have sort of an first in first out or deadline scheduler, the scheduler also implements two other queues. One of them is a read requests where all read requests are sorted in a FIFO queue, and write requests are also sorted in a FIFO queue. And if the request at the head of either the write FIFO queue or the read FIFO queue expired, so basically if the request has been there, if the request at the head of the read FIFO queue or the write FIFO queue has been lying there for 500 milliseconds or more, the default is 500 milliseconds actually, the scheduler then begins servicing requests from the FIFO queue. So basically what we're doing is that if I get lots of write requests, for example, and now they are being starved by the read requests, once 500 milliseconds have passed, the deadline scheduler will actually see that the write requests have not been serviced for 500 milliseconds, and then will actually start scheduling these before any other requests. Similarly for reads, and in case you basically have lots of requests coming in, then you will end up filling the spatial the spatial queue, which is sorted based on the physical location on disk, quickly before the deadline passes, and then you will do all your you're writing and reading based on that. The code for this was introduced for single queues in the beginning, but now it only exists for multiple queues, and the code for the multiple queue version of this is available in this link. Now, there was a complete fair queue scheduler. It was called the CFQ, and it remained as the Linux default I/O scheduler for a long while. Now this has changed, I think, since 2017. The BFQ I/O scheduler replaced the scheduler called the CFQ scheduler, and the BFQ scheduler is a budget-fair queuing I/O scheduler. It uses proportional share measured in the number of sectors. So when basically for each process gets basically assigned a number of sectors, and this is sort of their quota or their budget during some time. And this basically this enables since each process or thread gets a fraction of I/O throughput, then we are allowing all different processes and all different threads to gain access to the I/O device, thus making sure that there is fairness between the different threads and between the different tasks. This basically in addition, also the algorithm explicitly privileges the I/O of time-sensitive applications. These are basically interactive and soft real-time applications, and the algorithm has a mechanism to actually try to detect these soft real-time applications and interactive applications within the queue and service them before anything else. This is the implementation of the BFQ scheduler. Finally, there is actually some very good material on the BFQ scheduler by the designers of the algorithm on the first link in this page. You can go there, and they have all sorts of nice descriptions and tutorials and also performance measurements. The last scheduler we're going to talk about is called the Kyber I/O scheduler, and this is intended for fast multi-queue devices. So this is again an MQ, a multi-queue scheduler, sorry. And the idea is that basically the I/O requests passing through the Kyber scheduler are split into two primary queues. One is for synchronous requests, which are reads, and one is for asynchronous requests, which are writes. The idea is that basically reads are much less tolerant to delay compared to writes, because basically reads, many applications will block on read doing nothing until they read the actual data, but most applications would not block on writes and will not wait on the write operation to end. And the number of operations, both reads and writes, sent to the driver queues, to the dispatch queues, are strictly limited, thus basically making sure that you don't end up with an endless number of reads starving all the writes, or an endless number of writes starving all the reads, but rather always have them balanced. So limited sized queue basically. And there is very clean code with description in this link. So which I/O scheduler should you use? The only thing that I can tell you is that you should benchmark your application. One scheduler can be way better than another one in terms of performance, but in many cases, actually in many cases, if you do not do this kind of benchmarking, you might be fooled by basically some of the performance numbers that exist online, while it's actually in many cases a very close call. Sometimes it's not even clear why should you use one I/O scheduler over the other for many generic applications. Now we turn our attention to the second part of the lecture, which is closely tied to the first one, which is basically the Linux virtual file system. We were talking about the block I/O, which is basically the I/O scheduler and the block devices. Both of them are way down in the system. But then the virtual file system provides an interface between a Linux user and the various file systems that Linux supports. So, unlike many other systems, and unlike even older operating systems, there is a deeper need to be able to support multiple different file systems in a Linux installation. The VFS is basically a substantial piece of code. It's not just an API wrapper, but it basically provides sort of a level of abstraction between the user and the different file systems that the user can use. It has many applications and many functionalities. One of them is to cache the file system metadata. It coordinates data caching with the page cache, which we talked about in the last lecture. It enforces a common access control model between the various different kinds of file systems that Linux supports, and it actually implements complex common routines such as path lookups, file opening, and file handle management. We'll also very soon talk about different functionalities for the VFS, including supporting special file systems like the PipeFS. So, why do we have different file systems in the first place? A file system is in essence a hierarchical storage of data adhering to a specific structure. You're trying to use it to represent and manipulate data, files, and folders on the computer. However, we have different file systems because each file system tries to cater to a different audience. So there are different optimizations for each file system depending on their goal. Some file systems are more optimized towards storage. Some others are more optimized towards fault tolerance, for example. There are also differences in their capabilities, basically the largest size of the file that they can hold, or the largest number of files and directories that they can have. Some file systems are optimized for some more specialized hardwares or specialized storage systems. There is actually a very good list of all the file systems most of the file systems that exist today in Wikipedia, and a good comparison between these different file systems also lives on Wikipedia. I again need to remind you that the file system is mounted at a specific mount point in a global hierarchy known as the namespace. The primary objects of the VFS, of the virtual file system, many of them you have actually talked about in the Minix lecture. The first one is the super block object, which represents a specific mounted file system. The inode object, which represents a specific file. The entry object, which represents a folder basically, or a directory entry. And the file object, which represents an open file as associated with a process. There are lots of similarities between the Minix and the Linux virtual file system, and many similarities between what you see in Linux and what you typically study in an undergrad operating systems class. There are special file systems in Linux, and these I'm not even sure if they exist in Minix. And these enable the administrator to manipulate some of the kernel data structure and to implement special features for the operating system. One of these example file systems is the BDEF file system, which is basically the file system for block device drivers. So block device drivers, they exist in a file system space. The PipeFS special file system, which exists for pipes. We'll talk about it in more details in a little bit. And the proc file system, which is mounted on /proc, and this acts as a general access point to kernel data structure. So let's talk about the pipefs as an example special file system. Pipes have existed in Unix systems forever. They are a way for inter-process communication, and they have been very popular since their inception, basically. A pipe is a one-way flow of data between processes. All data written by process to the pipe is routed by the kernel to another process. Basically, a pipe provides you a pair of file descriptors, one for read and one for write. A parent creates a pipe, fork, then communicate with the child. This is all supported by the pipe file system. It's again, as I said, a special file system that exists and that is actually very well integrated in the VFS. Okay. It is implemented as a set of VFS objects which have no corresponding disk images. Then the implementation of pipe is in the link that you see in this slide. Let us look at how pipes work in more details. First off, let's look at a general anatomy of pipes. Pipes may be considered open files that have no corresponding image in the mounted file systems. So a process creates a new pipe by means of the pipe system call, which returns basically two file descriptors. The first file descriptor is for reading, and basically you can read from that file descriptor using the read system call. And the second one is for writing, and you can write to that file descriptor using the write system call. The process passes these descriptors to its descendants through the fork system call, thus sharing the pipe with them. So let's look at a more concrete example. ls pipe more. What happens when you call ls pipe more is that in the beginning the shell does the following. It invokes the pipe system call because it sees that there is a pipe. It interprets the pipe basically. Let us assume that the pipe returns two file descriptors. The first one is file descriptor 3 and the second one is file descriptor 4. 3 will be for your read channel and 4 will be the write channel. Now it will invoke two fork twice. The first fork generates a child process that executes the ls program. The second fork generates a child process that executes the more program. And it then invokes the close system call twice to release the file descriptors 3 and 4. Now the children, when they start their operation, first the first child, which is the ls program, performs the following operations. It copies file descriptor 4, which is the write file descriptor, to one of its own file descriptors, which it calls file descriptor 1 for simplicity. From now on, file descriptor 1 refers to the pipe's write channel basically. So it kind of makes an alias, or makes a copy, or hooks a new file descriptor to file descriptor 4. It invokes the close system call twice to release file descriptors 3 and 4. It no longer needs them. It has file descriptor 1. And it invokes the execv system call to execute the program. This is basically how the program runs. And the program ls writes its output to the file that has file descriptor 1, which is the standard output. It writes that into the pipe. Now, the second child process must execute the more program. And what happens here is that again it invokes dup to copy file descriptor 3 to its own file descriptor 0. And from now on, file descriptor 0 refers to the pipe's read channel. It invokes the close system call twice to release for both file descriptors 3 and 4. So it closes both of these file descriptors. And it invokes the execv system call to execute more. By default, that program reads its input from the file that has file descriptor 0, the standard input, and it reads from the pipe. So now that we have covered one of the special file systems, let's quickly glance over one of the less special file systems, one of the normal Linux file systems that Linux has had for a while, and this is extended thread, ext3. ext3 is basically built on ext2, which was built on ext1, and now there's ext4 that is built on ext3. And ext3, some of the main ideas that ext3 provides is that it supports immutable files. This is actually part of ext2 also. These are files that cannot be modified, deleted, or renamed, and they are append-only files. Also, the file system pre-allocates disk data blocks to regular files before they are actually used. Basically, when the file, making it much easier to increase the file size without any issues, as there are already several reserved physical blocks. And this also allows the file to grow more organically with no fragmentation. The file system also partitions disk blocks into groups. Each group includes data blocks and inodes stored in adjacent tracks. Basically, this allows the system to lower average disk seek time. Finally, one more idea is, and this is actually special to ext3, is that it's a journaling file system. And journaling avoids the time-consuming check that needed to be automatically performed on a file system when it was abruptly unmounted. For example, as a consequence of a system crash or a hard reset of the system. In fact, most of the difference between ext3 and ext2 is in the failure handling, and this is basically the main idea behind the ext3. Yet again, Linux need to support both ext2 and ext3 file systems. Now we turn our attention to the final part of the lecture, which, as I said, is a little bit of an oddball, and that is signals. Signals are basically the opposite of interrupts. They are a way for the kernel to send a signal / an interrupt to the applications, to the user programs. A signal is a very short message that may be sent to a process or a group of processes. The only information given to the process is usually the number identifying the signal. And there are a number of pre-identified signals that Linux and most Unix systems have. In standard signals, you do not have arguments, you do not have a message, or you do not have any other accompanying information. For example, one of the most popular, or some of the most popular signals is SIG.io, for example, which tells the user process that IO is done, or SIGKILL, which basically orders or forces all processes to exit. And signals are basically a set of macros whose name starts with the prefix SIG, and this is how many of them are probably very well recognizable for many of you. Signals serve two main purposes, one of them to make a process aware that a specific event has occurred, and the second one is to force a process to execute a signal handler function included in its code. And a process can change how it handles certain signals. So it can use a different signal handler function from the one that is already implemented in the kernel. It can use the kernel default. It can ignore the signal, and it can block the signal, which basically means that it does not deal with the signal now. It just blocks it, and it will deal with it later. These are some of the some signals. There are way many more. And you can actually read more about signals and I mean in many places, including obviously Wikipedia, but also in the second book that I have added today. So some of the features that the kernel needs to think about to implement for signals to work correctly. First of all, signals may be sent at any time to a process whose state is usually unpredictable. So signals are just like interrupts, but they go the other way. Signals sent to a process that is not currently executing must be saved in the by the kernel until that process resumes execution. So if that process is sleeping, the signal is not just going to get lost. The kernel distinguishes between two different phases related to signal transmission. The first one is signal generation, and that is when the actual signal is generated from inside the kernel. And the kernel updates the data structure of the destination process, basically the task struct, to represent that a new signal has been sent. Signal delivery is a whole different issue though, because if the process is sleeping or the task is sleeping, then you cannot basically deliver it until it wakes up. So the kernel forces the destination process to react to the signal by changing its execution state, by starting the execution of a specified signal handler or both. Signals are consumable resources, so once they arrive to the application, they no longer exist in the system. So the kernel must remember which signals are blocked by each process. When switching from kernel mode to user mode, check whether a signal for any process has arrived. This happens almost every time there's a timer interrupt, so once every 10 milliseconds if you were working with 100 Hz. Determine whether the signal can be ignored, basically either based by the on the implementation of the actual application or due to something else. Handle the signal, which may require switching the process to handler function at any point during its execution and restoring the original execution context after the function returns. This is how the kernel data structures for signals look. They are actually mostly defined. The kernel data, these kernel data structure are mostly defined in signals underscore types.h and the signals.h. And these are basically the different signals as stored in the system. With this, we conclude the last lecture, and we really hope that you guys have enjoyed the course. If you have any questions, please do send them. We hope that you stay safe, you and all your loved ones. Thank you, and well, I don't know when we will see each other, but stay safe.